Well, first of all, a great pleasure for me to be part of Red 16 and to thank Muriel and Hervé for all the organization that goes into making something like this come together. And as Muriel said, I've become very interested in this origin of life question. I'm a chemist, a theoretical chemist, and for many years, decades in fact, worked on different problems of chemical reactivity, why some reactions are fast, some are slow. Many aspects of chemical reactivity still haven't been fully understood. And then about 15 years ago, it suddenly struck me that the most interesting, the most fascinating problem in chemical reactivity is biology. I mean, we don't think of biology as part of chemistry, but because we now believe strongly that chemistry became biology, we have to understand how could that have happened, because it's still a very strange transformation that took place. So that's the background, and as I say, a wonderful problem, and I want to discuss that with you. And I won't be giving you, the overview that I'll be giving you will definitely be very much a personal perspective, one that has grown over the past 15 years since I became involved in this question. So the topics I'm going to cover are those shown here. This is just for the record. We don't have to go through this. I understand it's going to be on the web or wherever, so this is just what I want to be covering. And here we can start with the story. We all know, of course, that matter is made up of molecules: water, methane, sodium chloride, some fancy molecules like C60, fullerene, molecules. That's what chemistry is about. And of course, all living things are made of molecules as well: amino acids, sugars, fatty acids, nucleic acids, DNA there. But of course, we all understand that the molecules of life are not in themselves alive. So the question is, whatever the molecules were, how did those molecules become biology? How did chemistry become biology? And the transformation is a remarkable one, in that a molecular system, something, whatever it was, 10 to the minus 21 grams, as relatively simple, became this molecular assembly, which is 9 orders of magnitude larger, a very complex system. Now, 9 orders, 9 just sounds like a number, but what it means in real terms is that the equivalent of something the size of a pinch of salt became the size of several hundred elephants. So we went through an enormous transformation in complexity to go from here to here. How did that happen? And maybe more importantly, why did that happen? Okay, the origin of life problem, which I want to discuss, actually has many facets, and this is part of what makes the problem a little difficult. There's the where problem. What was the location on the early Earth? And one might think of that as a geochemical problem. How did it happen? What was the chemical path taken? One could think of that as a chemical problem. Why did it happen? Was there a driving force for the process? Is there a physical basis for this transformation having taken place? And one can think of that as a physical problem. And then there's the historical question: when did it happen? If we know when it happened, maybe it can help with the where, how, and why. And of course, the very fascinating question that we all want to have an answer to is, are we alone? How hard or easy would it be for life to emerge in other contexts? And of course, all of the answers to these questions maybe would give us some insight into that very dramatic question that we would love to know: are we alone? Just it's of interest to point out here that from the Kepler space mission, it seems that in our galaxy alone there could be as many as 40 billion Earth-sized planets in habitable zones. So at least from a statistical point of view, one can't help believing that the chances, given that it happened on Earth, that it's hard to believe that it couldn't have happened elsewhere. Before we look at this in any detail, we have to get one thing out of the way, and that is panspermia, the idea that life reached Earth from outer space. This idea was, I think, first proposed by a Swedish chemist, a well-known one, Arrhenius, in the early 20th century, and the idea there that spores were driven by light from another sun and landed on Earth. I don't think this is considered very likely, but it's quite remarkable to see that two great scientists, Francis Crick and Leslie Orgel, Crick of Watson and Crick, in 1973 wrote a serious paper in which they raised the possibility of directed panspermia, which is different from just panspermia in that some intelligent life actually sent life seeds onto our planet, and basically, if you like, trying to, we can think of it as colonizing the universe. I think Leslie Orgel backed off from this idea subsequently, but even though today we don't give this idea too much credence, but the serious problem with this suggestion is, even if it is true, it doesn't solve the problem. It just switches the problem from one location to another. The question then becomes, so how did life emerge on that other place, wherever it was? So in any case, as we will see as I go along, there's considerable evidence that life did begin on Earth from abiotic beginnings, and that's what I want to explore with you now. Okay, the when, the historic question. We know that the Earth was formed roughly 4.6 billion years ago, and it went through some dramatic changes, and that time period is divided into eons, reflecting the significant geological and biological changes that took place, events that took place. If we divide, we think of this period as a 24-hour clock, then life is thought to have begun about 3.8 billion years ago, something like 4 hours into that 24-hour day. Multicell life, us, and of course many other living things, actually began much later, something like 20 hours into that day. And us humans, we only appeared on the Earth at 1 minute to midnight. Okay, so we haven't been around very long in terms of the Earth's history. We believe that life, the basis for believing that life started off very early, there is good evidence for it. The first evidence, which is a little bit more tenuous, comes from radioactive dating, taking us back 3.8 billion years from the classic work of Moises in 1996, where he found in certain old rocks that the isotope ratio, C13 to C12, was low, which is typical of living systems. Life, for kinetic reasons, prefers to use carbon-12 as opposed to carbon-13. So if one finds a low isotope ratio, this is indicative of biotic origins or biotic material. But of course this is very indirect evidence, and one can't entirely rule out the possibility of some other explanation for the low ratio. There was no direct evidence for living material. We're just talking about the carbon isotope ratio in certain rocks. But the more definitive evidence comes a little bit later, still a long time ago, 3.5 billion years, from the fossil remains of stromatolites, which are these very special formations, rocks that show a distinctive structure of layers of cyanobacteria and sediment. And here you see a picture of a fossil stromatolite. And the remarkable thing is that these fossil stromatolites don't look too different to living stromatolites. Here is a picture of some from Western Australia, and I guess many of you here have heard about this is something quite well known to people who are in any way interested with the origin of life. The remarkable thing about these cyanobacteria is that they've, over such a long period of time, they've shown a remarkable conservation of morphology, so that if you look at the electron microscopy of fossil cyanobacteria, as shown in the top two pictures, they aren't too different from, and these are from very old rocks, they aren't too different to images of living cyanobacteria, and again that expresses the fact that the morphology was extremely well conserved over extraordinary periods of time. And this idea, we'll see, actually becomes very important as we go along, because I'll already say it now, the idea of persistence, this concept of persistence, is going to be very important in understanding what is life and how it came about. Okay, the where. Where on earth did life emerge? Maybe we can call that the geochemical problem. And here we're not doing too well. In fact, over the period since Darwin, we seem to have come round full circle. Darwin already had something to say about this. He speculated about a warm little pond and talked about ammonia and phosphoric salts, light, heat, electricity, etc. Sometime later, this idea was developed a little bit by Oparin, the famous Russian scientist, who talked about a primordial soup. But the important thing that he said there, he spoke about chemical evolution. In other words, there was some transformation, some change that was taking place at the chemical level that preceded the emergence of life. So we're familiar with the concept of biological evolution. There was an earlier period of chemical evolution. In the 60s, there was an interesting idea proposed by a chemist, a British chemist, Graham Cairns Smith, who said that life started on clay surfaces. A clay surface replicates in the sense that the surface is a template for the growing of the crystal. And he said at some point this template surface, acted as a template for biotic, organic materials, which was the beginning of organic replication till the point that the organic materials started to do the replication without that surface. I'm mentioning this one mainly for historic reasons, just the various ideas that have been proposed. And one might say that the flavor of the month, the very popular idea that seems to be current, is the one proposed already a couple of decades ago by Russell and Martin, amongst others, who spoke about hydrothermal vents as the place where life emerged. And here the idea is that we have effectively underwater volcanoes, which, in addition to the molten magma that is pushed out from the interior of the Earth, enormous chemical diversity of very reactive materials, molecules, hydrogen, H2S, hydrogen sulfide, ammonia, carbon monoxide, methane. So active, very reactive chemical materials, as well as an energy source, not just within those chemicals that come out, but the fact that in some of these vents the effluent is alkaline, which means that there is a pH difference between the effluent and the seawater environment, so that you have an ion gradient, a pH gradient formed, which can act as an energy source which is needed in life processes. So this is an idea that they've been pushing very strongly. Now, there's some criticisms of this, and this is why I say the stories come full circle. We're back to hot springs, which sounds a little bit like Darwin's warm pond. This idea has been put forward by Armin Mulkejanian, and here you see a hot spring, and this one here is the real color of the spring in Yellowstone, spectacular color. And the reason that he was critical of the hydrothermal vent idea was the fact that protoplasm, the stuff that we find in cells, is rich in potassium but poor in sodium, which is the very opposite of what we have in seawater. So he believed that seawater as the medium from which life emerged, it wasn't consistent with that. And he believed that these hot springs with maybe a richer concentration of potassium and a lower concentration of sodium was more likely. But there's a lesson in all of what I've been saying here, is that it's very difficult to give an answer to a historic question when the historic record isn't there to give a definitive answer. And the problem is, with regarding where life began, we don't have a fossil record for pre-life, so we don't really know where life began. It's a historic question, like a historic question, not a very interesting one, is what I had for breakfast on my 18th birthday. Now, no one really cares, but the only way one could know that tens of years or hundreds of years after is if there's a historic record. For example, if I would have written a diary and said, on my birthday today I had bacon and eggs and pancakes, okay? But if there is no historic record, then it's going to be very difficult to get a definitive answer. And therefore, the problem is that one can put forward hypotheses, but often these hypotheses aren't falsifiable. So person A comes up with one suggestion, person B with another suggestion, and it's hard to decide definitively which is correct, or maybe neither. Another problem is that, at least to date, no proto-life has been created by simulating presumed historic conditions. I mean, clearly if someone, as Martin and Russell in particular, has been trying to do experiments on hydrothermal vent conditions to see if something can be seen that shows a process that might reflect the beginnings of life's emergence, that would be terrific, but that hasn't been done as yet. So we're in a bit of a dilemma there, and one has to say that consideration of origin of life's likely historic location is, of course, very thought-provoking, and it's good to kind of pursue it from the point of view of thinking about how life, the conditions that might allow life to emerge, but ultimately, if one looks at it in too specific a way, it has to remain speculative. Let's now go on to the how question, the chemical path taken, the chemical problem. And here we're on slightly firmer ground because we know what life is composed of, so we can legitimately ask the question, how did life's building blocks arise in order for that process to have taken place? Now, life is fundamentally, we can say, a protein nucleic acid system within a lipid membrane. So proteins, of course, composed of amino acids and nucleic acids of nucleotides, and lipid membranes composed of lipids. So one can ask the question, how could amino acids, nucleotides, lipids have formed naturally with the materials that would have likely existed on the prebiotic earth? And the answer here is that it's not, maybe this is not a major problem. Prebiotic molecules, simple molecules such as the ones shown here, hydrogen, carbon monoxide, methane, ammonia, etc., formaldehyde, hydrogen cyanide, can react under the right conditions to form lipids, amino acids and nucleotides, and from them we can therefore move to the next step, vesicles from the lipids, amino acids to give the peptides and proteins, and the nucleotides to give RNA and DNA. Let's quickly look at some of this chemistry. Just an overview, quick overview, just to see what we're talking about. Okay, lipids. One of the advantages of the hydrothermal vent idea is that under those sorts of conditions, it's been shown that a mixture of hydrogen and carbon monoxide in those kinds of conditions with mineral catalysts can lead to the formation of fatty acids, lipid molecules with a long non-polar hydrocarbon chain and a polar head. And of course, such molecules are important because of their amphiphilic character, partly polar, partly non-polar, and in particular the characteristic that when one places such molecules, fatty acid molecules, in aqueous solution, you form a lipid bilayer because, of course, the non-polar tails want to be close together, and the polar heads want to be in the aqueous medium, either internally or externally. So you end up with vesicle formation through the aggregation of fatty acid molecules. So this is not unrealistic to have happened from prebiotic materials. Amino acids, well, actually the amino acid story is a very dramatic one because one might say that started off experimental prebiotic chemistry with the very famous Miller-Urey experiment. I'm guessing most of you have heard this, so I'll just go through it very quickly. Simply, if one takes a mixture of gases, as was supposed at the time, ideas have changed there, to have existed on the prebiotic earth, just simple molecules, and you heat up water as well, so you have water vapor in there, and then you put an electric discharge on this mixture, sparking, simulating, let's say, lightning. You end up with a mixture of a range of amino acids and other molecules as well, which is quite remarkable. Quite sophisticated molecules, if you like, from very simple beginnings, just through a simple experiment like this. And that, of course, was very dramatic at the time, and it seemed to pave the way. Okay, the origin of life, it's all easy now. One can make these the molecules of life easily, and therefore no problem for life to have emerged. Of course, it's not that simple, and the enthusiasm quickly subsided for reasons that I will discuss now. An interesting thing that was pointed out some years later was that the abundance of the various amino acids that were found in the Miller-Urey experiment, the relative abundance was found to be very similar to the relative abundance of these organic materials found in the Murchison meteorite that was discovered some years later, though I've also seen there's some criticism of this conclusion. But anyway, if this conclusion is right, then it seems to suggest that that distribution of organics is in some way general rather than the result of a specific experiment that Stanley Miller conducted in 1952. But regardless of that, the point of this experiment is that molecules such as amino acids can arise under prebiotic conditions. Nucleotides. Where did these come from? Nucleotides are actually quite fancy systems. It's you have here, they're composed of 3 components, a phosphate group, a sugar, ribose, and a base, a nitrogenous base, in this case adenine, but there can be others. And if these link up, a whole set of nucleotides link up through a phosphate sugar backbone, you end up with the 2 famous molecules, RNA and DNA. So the question is, where do these components come about in order for the nucleotide to be available to make a DNA or an RNA? And one should mention it's not just the adenine base, but there are others that need to be formed as well: thymine, cytosine, guanine for the DNA bases. So one at a time, let's start with the phosphate group. That's the relatively easy one. Phosphate is just a mineral, a common one, and certain rocks contain phosphate, and the weathering of those rocks could release phosphate, so we don't have a problem with phosphate in the environment. The sugar is a little bit more complex. That's already a specific and quite a delicate molecule. Where could sugars have come from? Ribose in this particular case. And it turns out that the answer is relatively easily that the polymerization of formaldehyde, which is a basic molecule, a prebiotic molecule, leads to sugar formation, a whole mixture of sugars, but ribose as well. In fact, 5 formaldehydes, if you line them up, gives you a ribose, and this happens under conditions, the polymerization under conditions, basic conditions with a metal ion catalyst. And actually this reaction is a well-known reaction, been known for quite a while, the foremost reaction going back to Butleroff, 1861. And it's just a chemical process. I don't want to go through it, but 2 formaldehydes join up to give a 2-carbon entity. Another formaldehyde joins in, 3 carbons, and the chain extends. And of course, once you have a sugar linear molecule, it can cyclize into the more typical cyclic form of the sugar. So sugars are, even though one has to say that the foremost reaction leads to very complex mixtures and low yields, they are possible to obtain through a prebiotic type reaction. What about the nitrogenous base? Where does it come from? And of course, we have to consider not just adenine, but the whole range of them. The one-ring heterocycles are the pyrimidines. There are 3 of these: uracil, thymine, cytosine, and the 2 purines, adenine and guanine. These are not trivial molecules. Where could they come from? And then a remarkable experiment by Jean Aurore, already quite an old experiment, 1968, that if you line up 5 molecules of hydrogen cyanide, you can make an adenine. And in fact, by refluxing cyanide in water, you can get adenine. So again, this molecule is not out of reach when one thinks of prebiotic conditions. And other syntheses that could lead to pyrimidines, briefly I show a couple here. So if you take cyanoamide, which is a basic molecule, you hydrolyze it, react it with water, you get urea, a very basic organic material. And if you take cyanoacetylene, again a prebiotic type molecule, add water to it, you end up with cyanoacetaldehyde. And these 2 together condense to form cytosine, which is one of the nitrogenous bases. And then a reaction of cytosine, hydrolysis basically, reacting with water, eliminating ammonia, gives you uracil. So I guess all I'm saying here is that the appearance of the synthesis of nitrogenous bases under prebiotic conditions is not something that one should be amazed with. It's something that could easily have happened. There was one catch here, though, which was subsequently overcome, and that is that for many years, in order to make a nucleotide or a nucleoside, you have to join up the nitrogenous base and the sugar, let's say ribose and cytosine, to make cytidine. And it didn't work. Chemists tried very hard to just join these 2 up, and it wasn't found to work. And then just a few years ago, in a very creative experiment, John Sutherland's group in the UK found a way of making this cytidine nucleoside, not by joining the 2 components up, but by doing it in a totally different way, basically taking these 2 molecules here, cyanamide that I already mentioned and glycoaldehyde, to make this precursor molecule 2-amino-oxazole, and then in a series of steps one can get the cytidine. The lesson here was that the way we think about molecules, when we look at a nucleotide, we see phosphate, sugar, nitrogenous base. But nature, you don't have to look at it like that and say, well, that's what I see, I'm going to put them together in that same way. Nature may do it differently. It doesn't have to look at it in the way we look at it. And in fact, by looking at it in a different way, Sutherland was able to overcome this problem and showed that under prebiotic conditions, nucleosides could be formed. So we have, if you like, the elements from which one can make nucleic acids. So, but I've presented this so far as it's all good news, everything's good. But it's really, there's good news and there's bad news. The good news is what I've been saying, that life's building blocks are accessible through prebiotic chemistry. The bad news is that generally they're obtained in low yields in highly complex mixtures. That's the bad news. But there's even worse news there, which I haven't mentioned till now, and this is that there is a deeper problem there beyond the low yields. And it's this that I want to talk about, and I think this deeper problem is the true problem in the origin of life question. You see, let's say this, we've seen that the synthesis of life's building blocks is feasible, but combining the molecules of life does not make life. A dead cell has all the molecules of life, but it is dead. Even if you allow the appearance of all of these materials in high concentration, in high purity, putting them together doesn't create life. Life is not just a chemical state, it's a unique organizational state. There's something very special about life. And we see this, of course, in the fact that living and non-living states seem to follow very different rules of change. And I'll be talking about that in a moment. So if we want to understand life's creation, it's not enough to say, oh, I know how the building blocks came about. What is this unique organizational state? And more importantly, how did it come about? How do we get to that very special organizational state that we call life? And here we come to what I think is the crucial question, the why question. Now, I mean, some of you may feel uncomfortable. Why? Just asking the why question. But it's okay. You're allowed to ask the why question in science. You know, why, if I let this go, it'll drop. Why did this bottle fall? And you can then say, because of gravity. Why questions are okay. It's trying to understand underlying driving forces for processes. And when we ask in the origin of life context why, we're asking, was there a driving force? Is there a physical basis for a process that would take dead stuff and turn it into living stuff? And I'm going to try and show you that there is as we proceed. But before that, just to look at, to tell you what you already know, that dead stuff and living stuff are very different. Very different. And I mean, some of it is so obvious I don't want to even bother mentioning it now. But let me just say one thing, that the rules governing change in the physical and biological worlds are different. And that in itself is very puzzling. In the non-living world, the big rule is the second law of thermodynamics. It tells us how things change in the universe. We're always headed downhill towards uniformity, equilibrium, what the physicists call heat death. But in the living world, it seems we're going the other way. Instead of going downhill, we're going uphill. Natural selection, which is the big rule of the living world, seems to go in another direction. And if you want a reminder of what natural selection is about, here is a graphic reminder where the predator suddenly finds it's become the prey. This leopard going about getting ready for lunch. And in this other world, in this living world, we see instead of going downhill, we go uphill. We go uphill, diversity and complexity, to far from equilibrium states and reaching purposeful dynamic activity, very different to the heat death of the non-living world.
What do you mean by purpose?
Sorry?
What do you mean by purpose here?
If there's something that we really don't have time to go into now, but I think we all agree that one major distinction between living and non-living is that living things have an agenda. Non-living things don't have an agenda. Rocks and planets and atoms and molecules have no agenda, but we all understand living things seem to have an agenda. How could agenda purpose have emerged from a universe with no purpose. This is part of the origin of life problem that needs to be understood. Now, exactly related to that, the physicists, the great physicists and others of the 20th century were really troubled by this paradox between the living and non-living worlds. Niels Bohr in the 1930s, life is consistent with but undecidable or unknowable by human reasoning from physics and chemistry. That's pretty categorical. And Erwin Schrödinger in his famous book basically talked about undiscovered laws of nature. To a physicist, biology doesn't make sense. That's what it comes down to. It shouldn't be, okay? And Karl Popper, the famous philosopher of science, said something quite remarkable. An impenetrable barrier to science and a residue to all attempts to reduce biology to chemistry and physics. Don't even try and explain biology in terms of physics and chemistry. And from Popper, that's quite an astounding statement. And Ernst Mayr, one of the great biologists of the 20th century, evolutionist, he basically spoke a lot about the autonomy of biology. He actually described a separate philosophy of science for biology as opposed to that for physics and chemistry. But we should all feel uncomfortable with that. Nature is one, and we have to somehow try and see how things are related, how they integrate. And if we believe, as we do, that life emerged from non-life, then there has to be a connection because it happened. Dead stuff became living stuff, so there has to be this, we have to be able to have a way of looking at the two within one framework so it all makes sense, okay? And just one other well-known biophysicist, Stuart Kauffman, who in his 2000 book wrote, maybe there's a fourth law of thermodynamics that we haven't discovered. Okay, so there's something fundamentally missing. Nature of change in the living and non-living worlds are very different. Now, one possibility that we have to contemplate is that it just happened by chance. Suddenly, all of a sudden, the materials of life just clicked, even though it was a very small chance, just clicked into the right position and we got life, and then from then on it just carried on. In order to consider this possibility, we have to look at probabilities, and Morowitz already some time ago said that the probability of a bacterium coming together from its components spontaneously is 1 divided by 10 to the, I think that's 100 billion. Now, that is a very, very small number. In fact, it's so small that we can't even understand how small it is, and I'll show you how small it is by showing you a much larger number, which is still very, very small, and ask the question, how many, if we have an RNA made up of 100 nucleotides, and of course the nucleotides can have 1 of 4 bases, so the number of RNAs of base length 100 would be 4 to the power 100, and therefore the probability of having the right one is 1 divided by 4 to the power 100, which is 1 divided by 10 to the 60th. 10 to the 60th is a lot smaller than this number here, but I want to show you how small this number is. If you wanted to synthesize 1 molecule of each of those RNAs, okay, 10 to the 60th molecules, single molecules, and I'm going to give you a lot of time to do this, not a week or a month. I'll give you 1 billion years. Now that's very liberal, 1 billion years to do it. the weight of RNAs you would have to synthesize every day to make one molecule of each kind, the weight of RNA you'd have to make every day would be 40 times the weight of the Earth every single day for 1 billion years, and then you would have one copy of those 10 to the 60th RNAs. So that just shows you the immensity, if you like, of the space of replicator space, the immensity of that space, and you cannot get to the chances of getting to the right combination by chance is too slim to even contemplate. So what that must mean is that we have a directed process, and we have to try and understand what that directed process is. Something was pushing stuff in that direction, and the question is, what is that? So let's try and think in those terms, and if we look at this origin of life question in a traditional way, we sometimes write it this way: non-life in some chemical phase, mysterious chemical phase, became simple life. And once we had simple life, the biological phase began to make complex life, and this phase we understand broadly as Darwinian evolution. There are lots of arguments about the details of that, but broadly speaking, we're comfortable with Darwinian evolution. Can the chemical and biological phases be related? Is there some connection between them? And a new area of chemistry has evolved. I'm using the word evolution in what's happened with the subject, but a new area of chemistry has come about called systems chemistry. The term was only coined in 2006, which tries and discuss this issue. And the term systems chemistry is actually a play on words with the term, the more common, the well-known term, systems biology, which is a top-down approach. We look at the whole system and try to understand how all the bits work together to make that system do what it does. Systems chemistry is a bottom-up, where we're trying to understand how this all came about, starting from its simple beginnings. So basically, systems chemistry deals with, at least partly, with simple replicating chemical systems and the networks they establish. And if you notice there, I'm now using a word that I didn't use till now, the word replication, replicating. And as I say, this was really, it's just a number of years now since this area has become more established. And it all comes down to this: replication is a very special chemical reaction. Very special, so special that it leads to the emergence of another kind of chemistry, a totally different kind of chemistry that goes under the name of biology. And I'll try and show you how and why that comes about. So, what is this systems chemistry? Let's try and put it in some context. If we think of regular chemistry as the chemistry of non-replicative systems, and if biology involves complex replicative systems, then systems chemistry is a bridge between these two in that it deals with simple replicative systems. And in that sense connects between regular chemistry, which is non-replicative, and complex replicative. If we understand these simple replicative systems better, we may have a link that joins chemistry with biology. So what does the systems chemistry approach say to the origin, regarding the origin of life? And I think it says something here quite dramatic, that initially we begin not with just non-life, but with some simple replicating entity. And I'm not specifying what that entity was, because that's a historical question and I don't know. But and I'm not even saying it was a molecule. It may have been a small network of molecules, but some replicating entity. And instead of two phases, a chemical phase and a biological phase, it's actually one single physico-chemical process, and there's a driving force for that process, the drive towards greater stability. So what I'm saying here is that actually the process of emergence had an identifiable driving force, and the same driving force that we have in biological evolution. Now, if that sounds a little bit strange, it should, because everything rests on what do you mean by stability? And this is a key question, because stability, it turns out, is a very elusive term, more complex than it might seem, because when we say stability, we mean different things. And this is something that I'll have to explain as we move along. So let's start by saying some basic things about stability, the different kinds of stability that we know. We're all familiar with thermodynamic stability associated with the system's energy, and of course that's central to the second law of thermodynamics. So you have a gas in a cylinder and you open it up to another cylinder where there's a vacuum. Of course the gas spreads out between the two cylinders. We go from an unstable, we consider the first state unstable, and we go from unstable to stable. The reason, though, that this happens is, and that's the second law of thermodynamics, through the profound insight of Boltzmann in the late 19th century, that the reason unstable to stable is low probability to high probability. The reason the gas goes from this situation to that situation, that this is a more probable state and this is a less probable state. You all know that if you take a pack of cards and they're nicely ordered and you shuffle, you'll get a disordered state because of probabilities. And if this particular state has many possibilities, microstates we call them, as opposed to this one which has few microstates, this is more probable, and therefore you go from a less probable state to a more probable state, just as with shuffling cards. The second law is a profoundly important law because, in contrast to many laws of nature which are empirical, the second law of thermodynamics is a logical law of nature. It's mathematical. It has to be because of probability theory, okay? So that's important. So when we say less stable to more stable, we're saying less probable to more probable, and that applies not just to gases expanding within some container, but to chemical processes. So the reason hydrogen and oxygen react together to give water is because water, if you like, is a more probable state. It's probabilities. Even though this isn't sufficiently emphasized when this material is taught, I think. But, okay, that's one kind of stability, but there's another kind of stability we're very familiar with in chemistry, and that is kinetic stability. And this is not about energy, it's about time persistence. Kinetically stable systems can be unstable thermodynamically, but they're still stable because we're now talking about stability as something else, something that persists for a long time. If a married couple have been married for 50 years, you say they have a stable marriage, stable relationship. It's got nothing to do with thermodynamics. Maybe it does somehow, but we won't go into that. The persistence is a measure of, it's another expression of stability. So, in fact, with this hydrogen-oxygen mixture, we say it's kinetically stable. It can be kinetically stable because you can take hydrogen and oxygen, and if there's no spark and no catalyst, they don't react to give water, and that mixture therefore is stable even though it's unstable. So it's unstable thermodynamically, but it's stable kinetically. So that's well understood. in chemistry. So, but it's important now to recognize that stability has two facets, and this will be critical to answering some basic questions which we'll be doing in the second part of the lecture. But just right now, stability is also reflected in a system's persistence and not just in its energy. You have two measures or two facets to stability. But it turns out there are two kinds of kinetic stability. The classic one, the one that we're familiar with that I mentioned, the static one, the hydrogen and oxygen mixture. And it turns out there's another one, a dynamic one, which is associated with certain replicating systems. And this one, I've called this one dynamic kinetic stability. It's associated with the stability of things that are persistent because they are good at making more of themselves. So if something is good at making more of itself, it'll be persistent. And remember those cyanobacteria that I said are relatively unchanged for maybe 2 billion years? That's persistence, 2 billion years. That's persistence, and it's a persistence associated with replication. But more on that as we proceed. But to understand this kind of dynamic kinetic stability, we have to talk a little bit more about replication. And replication starts, the simplest replication we can think of is molecular replication. It turns out that certain molecules are able to make copies of themselves. That's just a fact, and we call these, not surprisingly, replicating molecules. They're generally chain-like in structure, so RNA, DNA, so a long chain with a backbone, and in this particular case, the RNA, DNA, you have the bases that distinguish the building blocks from one another, and we have 4 different kinds there. Okay, that's familiar. But the point is that if you take RNA, and you can do this in a test tube, you take RNA in a test tube, add its building blocks, free building blocks, activated so that they will react. I don't want to get into the chemistry there too much. And we have to cheat a little bit and put in an enzyme, but again, that's not crucial to the experiment. RNA with its building blocks, under the right conditions, give lots of RNAs. Now, there's nothing mysterious about that because the mechanism is relatively well understood. It's a template mechanism. Here you have the original molecule, you can call that the template, this one here, and the building blocks floating around simply latch on in a complementary fashion to the original molecule. So there's an attachment there, and you end up with another replicating molecule, except you'll notice that the replicating molecule is not exactly the same as the original molecule. It's the complement of it. If this is the positive, this one is the negative. But if the negative then makes a copy of itself, you end up with a positive, okay, because of the complementarity of the recognition between those bases, okay. So this has been well understood for quite some time, and this very simple experiment was done by someone who, I mean, they really should pull him out of the grave and give him the Nobel Prize, despite the rule you can't give Nobel Prizes to dead people. He did this experiment in the 60s, this replicating molecule making copies of itself in a test tube. Okay, so molecules can make copies of themselves. Big deal. So what? I mean, methane reacts with oxygen to give carbon dioxide and water. Thousands of reactions in chemistry. And some molecules, you put in their building blocks with the molecule and they make copies of themselves. What's so special about replicating molecules? And the answer is they can be autocatalytic, meaning they can exhibit exponential growth. So that if one molecule doubles 79 times, it becomes a mole, the Avogadro number of molecules, because 2 to the power 79 is the Avogadro number. And if, in principle, if that molecule were to continue doubling for another 83 cycles, you generate a mass equivalent to that of the Earth. So a molecule just doubling about 160 times, in principle, obviously it's going to run out of resources, would give you the mass of the Earth. Now, that simple idea was understood already more than 200 years ago, Thomas Malthus in his essay on the principle of population, but the implications of that haven't been, in my view, fully appreciated, and just following through on that simple idea, we'll soon see that it leads to what I'm saying is this other kind of chemistry that we call biology. I want to show you another example, though, that shows the awesome kinetic power of replication, a kinetic example, because it's very instructive. I want to compare catalysis with autocatalysis. Here I've got a reaction where A plus B plus C catalyzed by X gives Y. And I'm now asking the question, if I have one molecule of catalyst, one molecule of X, and a reaction rate of 10 to the 6th molecules per second. In other words, this one molecule works very hard and can make every second 1,000,000 molecules of Y. How long would it take for this reaction to generate a mole of Y, to make 1 mole of Y from a single molecule of catalyst? And the answer is 20 billion years, a very long time, because Avogadro's number divided by 10 to the 6th, that's the rate, it's 6 to the 10 to the 17th seconds. And that's 20 billion years, which is much longer than the age of the universe. Now that same reaction I'm going to do not catalytic, but autocatalytic. So now A plus B plus C catalyzed by X makes X. And exactly the same rate, 10 to the 6th molecules per second. How much time would you need to generate a mole of X in this case? Does someone, it's going to be quicker because we're making more catalyst all the time. Does someone want to hazard a guess? Sorry? 1,000 years? 100 years?
1 year.
1 year? 79 microseconds. 79 microseconds. Why? Very simply. 2 to the power 79 is the Avogadro number. Each reaction takes a microsecond, and you need 79 reactions for a mole. So 79 microseconds makes a mole. That's autocatalysis versus catalysis. So catalysis, 20 billion years. Autocatalysis, 79 microseconds. Do you see the power, the kinetic power of replication? It is awesome. And this has consequences. This beautiful example was pointed out by Lifson in 1997 in the classic paper in the Journal of Molecular Evolution. So the point is that autocatalysis is an extreme expression of kinetic control, and replication is unsustainable. That's the important thing. It's unsustainable. And what that means is it leads to a different kind of stability, which is this dynamic kinetic stability that I've been mentioning. And the only way a replicating system can be stable, therefore, is if its rate of replication is balanced by a rate of decay. In other words, you're making it and it's decaying, so that you have a steady state of replicators that is persistent over time. Because you can't keep making them, we see that just goes crazy, okay? It gets out of hand. So that can be expressed with a very simple differential equation. The rate of formation of the replicator is given by a kinetic term here, the rate of a kinetic rate constant, times the rate of the concentration of the replicator, times the concentration of the building blocks. Let's say 1 building block for simplicity. And that's a second order term. And there's a rate of decay, which is another rate constant, G, the decay, times first order in replicator. And this is not terribly fancy stuff. Lotka, 1910, okay? The point is, when dx dt equals 0, that would define a steady state population when the rate of formation and the rate of decay are in balance. And to understand this in pictorial terms, let me show you this picture of a fountain. Here you see this fountain. This is the one in Geneva, and it's persistent. You come to Geneva, whenever you go to Geneva, there it is. It's still there, doing what fountains do, spurting out water. But, of course, the water in the fountain is different all the time. It's not the same water. The water is turning over. So when you have a steady state population of a replicating population, the population is stable, but the entities that make up that replicating population are turning over all the time. They're different. And this is quite important. And that's why we call this kind of stability, it's a different sort of stability to thermodynamic stability where the thing just sits there. This is a stability that is a dynamic stability, and it's not thermodynamic, it's kinetic because it's based on these kinetic terms here. The extent of its stability depends on the kinetic terms. So we have here dynamic kinetic stability, which emphasizes not the thermodynamic stability, but the stability as persistence, okay? And I just said that, it's called dynamic kinetic stability because the entities are turning over and it's the population that is stable. In order for this DKS state to exist, there is a number of prerequisites. The reaction making this dynamic kinetic state has to be irreversible, it has to be far from equilibrium, and it has to be energy consuming. In other words, there has to be an energy source for that to happen. And I want to just quickly show that, and maybe that will be a good spot then, well, we'll see, to have a break. Why must the reaction be irreversible? The reaction that we have, the replication reaction, is basically the building blocks, written here as reactants, plus the replicating entity, making two replicating entities. In other words, the replicating entity as a template makes a copy of itself. Now, if that's an equilibrium reaction, just going backwards and forwards, then the graph of the concentration of the replicating entity as a function of time would look like this. You'd approach equilibrium, okay? Now, if it's approaching equilibrium, you have an equilibrium constant, which can be expressed as just the rate of the concentration of the replicating entity divided by the sum of the concentration of the reactants. But there's no exponential growth. It'll just level off until you get your equilibrium concentration of replicators. Not very interesting. However, if we do the reaction irreversibly, only in one direction, then the thing goes crazy, as I mentioned earlier. We get this enormous kinetic power coming about, and you end up, and therefore the system, because it's not reversible, it's far from equilibrium, and it has to be energy consuming. It has to be energy consuming in the same way we're back to our fountain. That fountain is turning the water over all the time. Do you know that fountains, if you turn off the power, the fountain stops? In the same way, if you want this replicating process to continue, making replicators which decay, make it again, continually making and turning over all the time, you need a source of external power for that state to persist. So therefore, again, the reaction must be irreversible, far from equilibrium, and energy consuming. Now this is important because if you want to start to think about making proto-life something in the direction of a living system, we're beginning to see there are conditions for that. You can't just add the things together, because if you do that, you're just going to, the rule that's going to determine what happens is the second law of thermodynamics. It's just going to go downhill. You have to somehow, and I'm not saying it's easy because it hasn't been done yet. Well, I'm not sure that till now people have been focusing on what is needed to do it. But even if you think about it, it's not a trivial problem. You have to create a replicating system that's irreversible, far from equilibrium, if you like, this replicating fountain to create it. And for reasons that I will explain shortly, that could lead in some exciting directions. So let me just now say, okay, you've made this fountain, big deal. So you've got this replicating fountain. Why? How is that going to lead to life or evolution? Once you have such a fountain, there's a natural direction of change. And it's easy to see what that natural direction is. And the direction is based on mathematics. Just as the direction in the thermodynamic world was based on mathematics. Okay? There the direction was based on the mathematics of probability theory in the second law, and here the math is different. Let's look at the math because it's very simple math. Let's say you have your replicating population, and we already saw that this is the equation that describes that population, the kinetic equation. And now let's say there's some change, a mutation, and you have now, instead of that replicator x1, you have a second replicator sitting there, x2. So that equation now applies to the second replicator. Now if you solve these two equations, simultaneous equations, the solution, the mathematical solution, comes out to be that one of the replicators disappears and the other reaches a steady state concentration as if it was alone from the beginning. Where S, I didn't define it here, but S is the rate at which building blocks are being incorporated into the system. So basically, the math of competing replicating systems is such that, and this is stuff shown quite some time ago by Eigen and Schuster, the kinetically more stable replicator drives the kinetically less stable one into extinction, and the result is evolution. The persistent replicators will tend to evolve towards greater DKS, or another way of saying it, the persistent replicators will tend to evolve towards greater persistence. Persistence will tend to increase. The one that is better, the better replicator will simply out-replicate the poorer replicators, and there'll be an evolutionary process to better and better replicators. And at this stage, I'm not saying chemistry or biology, I'm saying replicators, whether chemical or biological.
Can I ask a question?
Yeah.
I mean, you need an equation relating x1 and x2, right?
Sorry?
You need an equation relating x1 and x2 in this, because otherwise you just have two parallel differential equations.
No, if you now try and simply it's an exercise in kinetics to solve these two equations, the simultaneous state, the one solving these two equations as a kinetic exercise, you come out to two possibilities. Either the K1 divided by G1 equals K2 divided by G2, and then they can coexist. But that cannot be. You cannot have two replicators with exactly the same ratio of forward and decay rate constants. Okay, you can't. That won't happen because two numbers will never be exactly the same. So if you look at it, if you go into the math of it, you simply see for these two equations to hold simultaneously for dx dt equals 0, if you make these 0, each 0, and then solve the two, you end up with x2 or x1, it doesn't matter, becoming 0. In other words, the two replicators cannot coexist if they are eating off the same building blocks.
Yes.
But here I'm defining it to be that because M is the same in both cases. Okay, so it's the same building blocks.
Yeah, okay.
Of course. Because the building blocks can be different. I mean, this is why camels and bacteria aren't competing directly with one another. But there's in fact a law of ecology whose name I've forgotten, but basically say two species that feed off the same resource in the same environment cannot coexist. One will drive the other into extinction. So there's a biological equivalent of this chemical law. Okay. Now, theory is wonderful, you know, it's great theory, but it's nice if the experiment, if the experiment comes up with the same result, and happily it does. And I said earlier that if you put an RNA into solution with its building blocks, it makes copies of itself. But in fact, sometimes it makes copies incorrectly, mutations if you like, and one actually sees, so not only are copies made, but there is a mutation, so you start off with a slow RNA, which has a length of 4,500 bases. This was this wonderful experiment from the 60s, Spiegelman. And after 74 cycles, you end up with a much shorter RNA, which was really a fast replicator, and it was dubbed Spiegelman's monster because it was so fast, okay? So one can actually see the evolutionary process taking place in a test tube at the molecular level, reflecting the kinetics that I showed you in the previous slide. So I guess what I've been trying to say till now is that we're seeing, based on the math of exponential growth, that replicators, persistent replicators can only form steady states. They cannot continue to grow. And the process of mutation will lead to a situation of continual evolution, change in the replicator towards better replicators from worse replicators. So maybe this is a good point to stop, and if there are any questions or to clarify.